The final thing I want to discuss here, I introduced Dalton's law and now Raoult's law, is we could even combine them as well, right? And so let's say we combine Dalton's and Raoult's law, right? And so what we're going to get is, by combining them, what I'm going to do is I'm going to take the sum of all the partial pressures, okay, for a system with n number of chemical species, right? And so, from Raoult's law, we know that, well, actually, I'll say, if I sum up all the partial pressures in a chemical species, we know from Dalton's law that that's equal to the total pressure, right? From Raoult's law, right, we could also just plug in this relationship, right? So that our total pressure is also equal to the sum of the product of the mole fraction of the species I in the liquid times its vapor pressure. Okay? So that's, by combining Dalton and Raoult's law, we end up with this relationship. And I'm boxing this in because I want to emphasize that this is a very important equation. All right? This is a very important equation, and this is an equation that you're going to come back to, for the rest of your career. All right? So I want to emphasize its importance now. Just to give you an idea of what this would look like mathematically, if we consider a two-component system, what this would mean is that the total pressure in our system is equal to the mole fraction of species A in the liquid times its vapor pressure at some temperature plus the mole fraction of species B times its vapor pressure. And of course, since it's a two-component system, we know that 1 is equal to XA plus XB. Right? And so we could even combine the equations and reduce the number of variables there. You'll see why this equation is important once we start trying to calculate actual phase diagrams.